Hello everybody, myself Prasant Mukhopadhyay, faculty member Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In our last class of three-phase induction motor, so we have started with the rotor-induced EMF relation between the rotor frequency and the supply frequency, and say different say problem related to that rotor power factor, etc. And today, actually, the last class I told you that before we going to the stock slip characteristics of the three-phase induction motor, we have to know the basics things. So since we have got the idea about rotor-induced rotor current at running conditions, so we can jolly well find out the power developed in the rotor, and as a whole from this we can find out developed torque. That means the torque exerted on the rotor by the rotating flux. So with this we'll not go through the detailed discussions, and that is not say in our scope. So we'll directly go to the torque slip characteristics. And basically, as I told you, since we came to know the rotor induced EMF, rotor at running condition, rotor current at running condition, so and rotor power factor at that running conditions. So as a result, we can find out the power of the rotor circuit, and from that we can find out the developed torque. That is the shaft torque, or that is the output torque from the power and torque relationship. That is P equal to the omega into T. So from these equations we can find out there must be some step that is say air gap power in the stator. Then from that after different losses we'll get the air gap power in the rotor circuit, and from that we can find out the say developed torque of the rotor. So with this we'll come to the discussions of the rotor torque slip characteristics. And actually torque slip characteristics means it is a graphical representations of or curve drawn between the torque and the slip. That is slip, the value of the slip in between 0 and 1, as slip is nothing but the difference speed of synchronous speed and the rotor speed, and with respect to the synchronous speed, so its value can never exceed 1, and so it will lie between, and it will be from 0 to 1. So if whenever the synchronous rotor speed is nearly or almost equal to synchronous speed, then the slip will be 0, and at starting conditions it will be synchronous at 1. So rotor the slip start at s equal to 1 to synchronous speed at s equal to 0, and this the graphical representation of the torque versus slip is characteristics as the torque slip characteristics of the induction motor. And naturally, if we go to the torque equation, we'll find the torque will be proportional to this is the s e2 square r2 by r2 square plus s square x2 square. As you know, the E2 is the standstill rotor induced EMF, S is the slip, R2 is the rotor resistance per phase, and x2 is the rotor reactance per phase as standstill. So and input voltage, if it is a constant, so we can E2 equal to constant, so equations will be, if this is constant, so S R2 by this one. So from this we can draw the torque slip characteristics like this. So it will be like this for S equal to from 0 to S equal to 1, the torque will be like this. So it has three portions. So this one, this and this. So it is the stable region, it is the maximum torque or pull-out torque, and this is the unstable region. Okay, so this is ST. Okay, at n equal to s equal to 1, n equal to 0. This is the starting torque. So this is full load torque, and this is maximum torque. Clear? And this is maximum torque at maximum slip, s equal to sm. This is the at n equal to ns. N equal to ns means slip is 0 at synchronous speed, and it is the starting at starting, that is n equal to 0, that is equal to 1. So so this region way is the stable region of operation, and this is unstable region, and this point is the maximum torque point. The point B, this is the starting torque point, that is at s equal to 1, that is n rotor speed equal to 0, and this is the full load torque. So point C, this is the full load torque. Okay, so that is torque slip characteristics, and you see it has three regions as you are finding. That is stable operating region, unstable operating region, and normal operating region. Okay, the stable region, as I told you, this AB is the stable region. Okay, this is the stable region, and unstable region, operating region, this one, this is the this AB is the unstable region, and OA is the stable region. Okay, so and normal operating region, another is normal operating, so stable region. So here it is characterized as S is very small. If S is very small, then this Sx2 whole square is very less than R2 square. So hence this portion is neglected. So if this portion is neglected, so in the torque equation becomes like this: torque proportional to S R2 by R2. That is, S is R2 to cancel out, so torque is directly proportional to shape. It is like a equation of Y proportional to X. That is a equation of a straight line. So this is, as R2 is constant, we can say T is directly proportional to slip. So this is a straight line. In this region, as load increases, torque increases, slip also increases. Okay, so characteristic is approximately straight line, that is shown here, this one. Okay, wait. So this is your stable region AB. Then come to unstable region. This unstable region, when S increases further from maximum slip, the region is unstable region. So S is high between maximum S equal to Sm and 1. So R2 square can be neglected, as since S is high. So it no longer it will be S square x2 square is high in comparison to R2 square. So we can neglect R2 square. So torque is proportional to S by S square x2 square. So that will be 1 by S, as x2 is a constant. So in this region, when load increases, slip increases, but torque reduced. So 1 by S, it is T proportional to 1 by S is just like a approximately rectangular hyperbola. So this unstable region is BC, not BC, this one, AC, unstable region. So when S increases further, as I told you, when load further increases, rotor speed deteriorated or decreases, slip increases, and leads motor to standstill condition. Hence, the motor should not be operated at any point in this region. So this is called pull-out region. Okay. So normal region. So normal region is AD. low slip region. The motor can continuously operate in this region, and it is given eddy. No, not eddy is not region. This is the normal region. Okay. So normal region. Like this, we can have the torque slip characteristics. Low slip region, the motor can continuously operate in this region. So there are three torques. One is starting torque, maximum torque or pull out torque, and full load torque, TFL. So starting torque, the motor produces the torque when say slip is 1, that is speed is 0. Maximum torque or pull out torque, that is at maximum slip, the torque is the maximum torque. So this is called at maximum slip, the torque is maximum, so it is the maximum torque, and maximum slip is at which maximum torque occurs, so also called the breakdown or pull out torque. And full load torque, that means in this characteristic, the torque corresponding to the point full load torque, called full load torque of the motor, usually it is less than Tm. Actually, this is not shown here in this graph, but full out torque is written. This is not D. This is full out torque. Okay, so that's all about torque slip characteristics. So we'll then related some problem, we'll discuss about the torque slip characteristics losses, magnetic losses, that is magnetic losses, constant losses, mechanical losses, that was the constant losses, and electrical losses, that is variable losses. So magnetic losses also called core losses and or iron losses, and losses occur in stator core and rotor core because of the rotating magnetic field. And these are also two types: eddy current loss and hysteresis loss. So hysteresis loss can be occurred due to the alternate change in magnetic field in the stator core, and can be minimized selecting high grade silicon steel as the material. So and eddy current loss occur due to flow of eddy current to the body of the stator core, and can be minimized by using laminated construction of the stator core. And two losses depends on supply frequency, because stator supply frequency is the supply frequency, hence the iron loss for the stator is more, and since rotor frequency is less, hence iron losses are also very small, neglected to under running conditions. So mechanical losses, that is consist of frictional losses and windage losses. So frictional losses occurs at the bearing, and windage losses is due to the air gap, say wind at the air gap portion. So rotor has to overcome this the air resistance. So this is the windage losses, and losses are very less due to the speed drop is very small. So constant losses are of two types: iron losses and mechanical losses. And electrical losses due to the stator and rotor resistance, winding resistance, and these are also called copper losses. So when load increases or decreases, current increases or decreases, so it is this loss is called variable losses. And rotor copper losses for a three-phase equal to 3 I2 square R2 square. I2 is the rotor current and R2 is the rotor resistance per phase. So if we draw the power flow diagram, so like this, three-phase AC source, so input, this is the stator winding PI. So this is the air gap power after stator copper loss and stator core loss. So from air gap power, so rotor copper loss if it is deducted, we will get the mechanical power developed at the rotor shaft. So this is the shaft, and if we deduct the friction of windage losses or stray losses, we get the output power. So this is the power flow diagram. So actually what we are finding, so from the power flow diagram we'll discuss right now. So at the very beginning of the discussion of torque slip characteristics, I told you in short that how torque equation has come. That is how the power is being developed, and from power, from the relation of torque and power, we will get developed torque at the rotors. So it will be clear from the power flow diagram that basically we are supplying a three-phase AC to the stator winding, and so this is the input power PI. So from stator winding, the stator copper losses will happen, and stator core loss. So if we deduct this two loss, we will get the air gap power, because air gap means this is the from stator and rotor, in between the stator and the rotor. So this power is known as the air gap power, and this power will be then induced in the rotor winding. Rotor. So if we deduce the rotor copper loss and so mechanical power developed in the rotors, that is the rotor shaft, and if we deduct the frictional and windage stray losses, etc., so we will get the output power which will be available for the load. So how now come to the discussions how this power is being developed here. So from the power flow diagram, we are finding this induction motor convert electrical power into mechanical power, and three-phase supply is fed to the stator. So input power is equal to root 3 VL IL cos phi. This is the power factor. So losses occur in the stator, as I told you, the stator losses, that is PSL, and remaining power is transferred to the rotor magnetically. So it is called output of the stator or input to the rotor, that is P2. So this is the difference. P2 is the difference between the input power and the rotor stator losses. So in the rotor side, rotor copper losses occur. So if you from this rotor input power to, if you deduct this, so you will get the developed. So normally rotor iron losses are very small, and therefore it should be neglected, and remaining part is called the mechanical power developed. So that means if this is the rotor copper loss PCU, then rotor mechanical power developed is rotor power input power minus the rotor copper loss. So this is the mechanical power developed, and from here we'll get from the power flow diagram, due to rotating part in the motor, mechanical losses occur. So this is power output power will be mechanical power developed minus mechanical losses. So we can find out rotor efficiency, therefore rotor output by rotor input. So that is, this is the rotor output and this is the rotor input. So PM by P2. So motor efficiency will be mechanical power output at shaft by electrical power input to the stator, that is P out by P in. So this is the motor efficiency. So we'll found from to develop the torque, how the power flow is taken place from the incoming power to the stator to the final developed power at the rotor, and from hence we'll get the relationship, that is the efficiency of the rotor efficiency as well as motor efficiency. So that is output by input from relationships, that is rotor output by rotor input will give you the rotor efficiency, and motor output by that is the ultimate rotor output divided by motor input, that is electrical power input given to the stator. So from here we will get the motor efficiency. So with this we can find out the relationship between the rotor input and rotor copper loss and gross mechanical power. You know, in general, power in terms of torque is given, say P equal to omega times the Tz. So this is omega twice by n by 60. So power is transferred from stator to rotor. So this is equal to synchronous speed, angular speed. So P2 equal to Tz into omega s, that is this. So now gross mechanical power developed by the rotor is Pm equal to Tg into omega, that is Tg into twice by n by 60. So rotor copper loss, this is P2 by Pm, so this minus this, so copper loss equal to this. Okay, this is simple mathematics. Okay, now this, if we find out the relationship between rotor input, rotor copper loss and gross mechanical power, so it is the rotor copper loss by rotor input. So if we put these values, so we will get this is nothing but equal to S slip. So rotor copper loss is the slip time, the rotor input, and or we can say rotor input equal to rotor copper loss by S. And this mechanical power developed equal to rotor input power minus rotor copper loss. So if we put P rotor copper loss equal to SP2, then P2 equal to 1 minus S. So rotor copper loss by mechanical power developed equal to S by 1 minus S if we put these values. Again also this is the rotor input power equal to this. So from there you will get torque will be like this. So torque developed torque is proportional to the rotor power input. So torque in synchronous what will be? So it will be P2 equal to P Q by S. So this is equal to Pm by 1 minus S. So like this you will get the different relationship of the different power, rotor power, rotor copper loss, and gross mechanical power. So now we'll discuss some problems which will clear the our understanding much more. Let us take a problem. A 6-pole 3-phase induction motor develops a power of 22.8 kilowatt, including mechanical losses, which total 1.492 kilowatt at a speed of 950 rpm on 550 volt 50 hertz mains. The power factor is 0.88. Calculate for this load slip, the rotor copper loss, the total input. If the stator losses are 2000 watt, the efficiency, the line current, the number of complete cycles of the rotor electromotive force per minute. So let us find what are the data given. Equal to 6 pole developed power is mechanical developed 22.8 kilowatt. Mechanical loss is power loss is 1.492 kilowatt. Rotor speed 950 rpm, line voltage 550 volt, supply frequency 50 hertz, and power factor is 0.88. So slip is 120 F by P. As you know, the synchronous speed equal to 120 F by P. So if you put these values, you will get the synchronous speed equal to 1000 rpm. The slip equal to ns minus ns, ns minus n by ns. So you will get 5%. So now rotor copper loss, PC equal to P2 into 1 minus S. P2 equal to PM, again P2 equal to PM by 1 minus S. So PM is given, S is found, so this will P2. So copper loss, rotor copper loss will be S times P2. So you found P2 is this, S is this, 5%, so it will be 1.17 kilowatt. The total input power is how much? P2 plus stator losses. So P2 and stator losses equal to 2. Stator losses is given actually. This is stator losses is 2 kilowatt. Okay, so you will get this is the input power. So efficiency equal to output that is developed power minus losses, that is equal to this. So efficiency P out by P in into 100, so that is the motor efficiency. Okay, so that's all about the problems from the different relationship. Not only that, you will have to find out the line current, line current is equal to, this is the input power, power factor is given, input voltage is given, input power you have found. So from that you will found out the line current. So number of complete cycles of the rotor electromotive force per minute. So this is equal to F equal to S into F. So this is 2.5 hertz per second. So if you convert it into minute, 2.5 into 60, so 150 hertz per minute. So that was the problem given. So this is discussed. I hope you will understand it. Another problem we can take. It is a 37.3 kilowatt 4-pole 50 hertz induction motor, has friction and windage losses 3320 watts. Stator losses equal to rotor losses. If the motor is developing full load power output at a speed of 1440 rpm, calculate synchronous speed, slip, mechanical power developed by the motor, rotor copper loss, power transfer from stator to rotor, stator power input and efficiency. So data given, output power is given, pole is given, the supply frequency is given, friction and windage loss PML is given, stator loss is also given, that is equal to rotor loss PCU, and rotor speed is given. So synchronous speed from the equations we can find out, n is equal to 120 F by P, slip equal to ns minus n by ns, you can found. Now mechanical power developed by the motor is P output is equal to mechanical power developed minus mechanical losses. So the output plus this losses, that is equal to, this is the mechanical power developed, and rotor copper loss, so rotor copper loss by mechanical power developed equal to S, this relationship S by 1 minus S. So from here you will get the rotor copper loss that is given, that will found here, and power transfer from stator to rotor, it is PT equal to PM plus this rotor copper loss, that equal to how much, this plus this. So this will be like this. So power transfer, and stator power input is rotor input power by stator losses. So this will be like this. So efficiency equal to power output power by input power into 100. So this will come to this. So this is another problem. So that will clear your idea about the discuss relationship of the powers. Now another problem, I don't know whether we will finish it today's class or not. We have to continue in the next class also. So an 18 kilowatt 4-pole 50 hertz 3-phase induction motor has friction and windage loss of 500 watt. Full load slip is 4%. Compute for full load, rotor copper loss, rotor input, the shaft torque and the gross torque. So what is given? Output is given 18 kilowatt P output. Number of pole is 4. F equal to 50, and you have to you have given PML equal to 500 watt. S is 4%, that is 0.04. So rotor copper loss is the developed power equal to output power plus rotor loss, mechanical losses. So 18 plus this, so this is the mechanical power developed. So rotor copper loss equal PM into S by 1 minus S. So this, put the values, you will get this. Now rotor input equal to mechanical power developed plus rotor copper loss. Just add up these two you found. Shaft torque equal to 120 F NS, you know from this, and shaft torque is P output into 60 by twice by N. So this will be like this, and gross torque is PM into 60 by twice by N, also like this. So that's all about this different relationship and their problems we have discussed so far. That is in this class from torque slip characteristics and its related problem. And if you found any problem, you'll contact me. I'll